This lecture is about measurements, looking at different parts of a quantity, the properties, the units, precision and accuracy, and just the whole process of measurement. So measurement provides the information that's the basis of most of the hypotheses, theories, and laws in chemistry. And it's important that your measurement has this information. We need to know the size or magnitude of the measurement, so the number. We need a unit, and we need uncertainty of the measurement. Now, sometimes we're not as picky about this uncertainty, but it is important to realize that it is there. So without units, a number can be misleading or confusing. Like if I just said 5, and that was my answer, and I didn't have anything else after that. Do I mean 5 gumballs? Do I mean 5 cars? Do I mean 5 miles? So it's important to have a unit after it. 5 for meters. Now, if we were to look at these two rods using these two rulers shown, notice that they're both 10-centimeter rulers, right? We can see, though, that the increments on ruler A are less than in ruler B. There are more notches or markings on ruler B. So if I was to look at this rectangle rod, I don't know why it says candy cane, and if I said estimate the length of it, I would say, well, it's at least 4 centimeters. And I could estimate that would be about 4.5, so maybe 4.2 centimeters. So what's important is that we can be exact to the whole number here, and we could estimate one more digit. So if I were to lay a pencil on ruler A, and let's say the pencil went to here, so I'll just extend this guy, we would be able to estimate and say, well, it's 6 point, and then I would follow this down, maybe 6.8. But every measurement on this ruler would be measured to a tenth. I could say that I am accurate plus or minus 0.1 centimeters. That's a centimeter. So ruler B, however, if I look at ruler B and I follow this guy down, I would say, oh, I can be exact to the 4 point. I can see that it is 2, which is, these are in tenth increments. So I can say, oh, it's at least 4.2. And I can even estimate one digit further. I'm going to say that it's 4.25 centimeters. So I can estimate to the hundredths. I can be exact to the tenths versus ruler A, I was exact only to the whole number, and I was estimated to the tenths. Here, I can be exact to the tenths and estimate to the hundredth. So then I would say that I would be 4.25 plus or minus 0.0 to the hundredth. And same with if I were to take this top awful drawing of this pencil and follow it down, oh geez, follow it down, I would say that that is 6.567, 6.7. I'd say it's just, I mean, according to this line, it didn't quite touch the 0.8. So 6.79, I would say, centimeters. Again, plus or minus that hundredth of a centimeter. So pretty much what we just kind of summed up is that ruler A has more uncertainty than ruler B. Ruler B gives us a more precise measurement. Now, when we're looking at mass balances, if I were to want to measure the mass of a solid or a liquid or a gas, and I put it on this balance, that I can be, again, certain to the device that I'm using. So what's nice is with the electronic scale, you just write down whatever it tells you. With the triple beam balance, again, we would be limited to whatever my measurement here is. If it's, to the 10th of a gram, then I could estimate to the 100th of a gram. Electronic balances tend to give us a lot more precise measurements. Now, volume is the amount of space that's occupied by a solid, a liquid, or a gas, and there's several ways that we can measure that. Most common is by using a graduated cylinder. We would just take our liquid and we would pour it right into the graduated cylinder, and we would be able to measure from the bottom of the meniscus and see how much space it's taking up. You can, for much smaller quantities, use a syringe. For titrations, a burette is very common. Pipettes we often use in chemistry, as well as volumetric flasks. Now, counting is the only type of measurement that is free from uncertainty. So like we said when we're measuring a ruler or using a ruler to measure, there is some uncertainty to that. And our exact, like I said, counting being an exact, like if I had 5 quarters and I'm going to count those quarters, there's not an uncertainty to that. If I have a compound H2O and I said, well, there are exactly 2 hydrogens and 1 oxygen in this compound. That is an exact measurement. Also, defined quantities, like saying that 1 foot is exactly 12 inches. So 1 foot equaling 12 inches is an exact number. There's no uncertainty to that. It's not 1 foot is, about 12 inches or maybe 12.1. No. So same with saying in 1 inch, there's 2.54 centimeters. 1 gram is 0.001 kilograms. If I looked at these quarters right here, I would say that there's 1, 2, 3, 4, 5, 6, 7 quarters. There's not 8. There's not the possibility of there being 8. It's not like the slide where I said, okay, we could be exact to the whole number, and we're going to say, well, maybe there's 7.5 quarters. Maybe there's 7.2 quarters. No. Quantities derived from measurements other than counting are uncertain to different extents. So they're not exact. And there's always limitations of the measurements that we use, like that ruler. The ruler that only had whole numbers, we're limited by that ruler. We could only be accurate. We could only measure to the whole number and then guess to that 10th position. So the more precise of a measurement we use, then the less limitations that we have with that measurement. So looking at this example of volume, if I were to say, what is, how many milliliters of liquid is in here? So we would look at our graduated cylinder. We know it's in milliliters. And we can see here that we have measurements of 5, 10, 15. So the marks on the side of our graduated cylinder are going up by 1. So I would say, okay, well, this is 20 and that's 21. So it's 21. We at least know it's 21. We can be exact to the ones. But we can estimate further. It's not 22, right? And of course, we want to measure from the bottom of the meniscus. So we're going to say, okay, this is 21 right here. This is 22. I'm going to say that's 21.5 milliliters. So we can estimate that tenths position. We can be exact to the ones and estimate that to the tenths. Now, a measurement is said to be precise if it yields very similar results repeatedly. It's accurate if it yields a result that is very close to the true or accepted value. So here's some examples of when you could be accurate and precise. Think of hitting the bullseye. We know that the center of the bullseye is the ideal location. That is accuracy, is the center. So if you were to throw some darts and hit the bullseye and then hit really close to the bullseye and then another one that's not quite the bullseye but is really close, you are really close to that bullseye, so you're accurate. All of your measurements were really close to one another, so you're precise. Now in letter B, we can see that our three shots were really close to one another, so we're precise, but we were not at the bullseye. So we were not accurate, but our measurements were precise. And then if you look at letter C, our three measurements here are kind of all over the place. Not terribly all over the place, but I would not say that we are precise, and we're definitely not accurate hitting the bullseye. So if we were to look at these three sets of measurements from these dispensers, I want to look at number 1. We can see that they are precise because look, these are all 283, 284, 283, 284, 284. They're all very close to one another. So I would say that they are precise. But we know that our dispensers are 296 milliliters. So are we anywhere near the bullseye, the 296? I would say no. So we're not accurate. In dispenser 2, here we have 298, 294, 296, 297, 293. So we range from 298 to 293. That's quite the range. And there's only one of our measurements that hit the 296. So, I mean, we're closer to being accurate. Yes, we're more accurate, but we are less precise. They're kind of all over the place. Now let's look at dispenser 3. 296, 295.9, 296, 296, 296. Wow. So these measurements, I would say, is both accurate and precise. How would you classify these? Pause for a minute and tell me what you think. So this last set of exercises, I would look at these targets and say, well, they are definitely close to being accurate. I would not say that those 4 are precise, but I would say these are more accurate, less precise. For Archer X, these 4, those are pretty close to one another. I would say precise, but they are not accurate. They did not hit anywhere near the bullseye. For Y, these 4 shots, definitely not accurate, definitely not precise. Same with Z. Not accurate and not precise.